Hi, everybody. This is Unit 3 or Module 3 we're starting today. And in Module 3, we go over a couple of things that are somewhat important. We go over rational functions, and we deal with inverse functions along with logarithms and exponential functions. So we're going to start out with rational functions. So let's take a look. I sent out a handout on rational functions last time. So let's take a look at that handout. So let me share that screen with you. And this is what I sent out to you. Taking a look at this, let me go up to the top. So first off, what is a rational function? A rational function is a function that's a polynomial divided by another polynomial, where the denominator, the g of x in this case, cannot equal 0. The domain of a function is defined wherever x, for whatever x, where g of x, the denominator, does not equal 0. Two things can happen when you look at places where the denominator equals 0. One thing is that there could be a hole in the graph. Okay? The second thing is that there could be asymptotes. We're going to look at both situations. So let's look at the case where we have holes in the graph. How do we know there's a hole in the graph? Well, we take a rational function, and if we can factor the top and bottom and divide out any places that would make the denominator 0, that means that there would be a hole in the graph. So for example, I have a rational function here of the quantity x minus 2 plus the quantity x plus 3 over x plus 3. Now the numerator is already factored. We really can't factor the denominator. It's x plus 3. So we could actually divide these two portions out, the x plus 3's, leaving us with just x minus 2. But we can't just divide it out and ignore the fact that we started with x plus 3 in the denominator. So first off, the domain would be anywhere from negative infinity to minus 3, union minus 3 to positive infinity. Why? Because that makes x, for x equal minus 3, x plus 3 would be 0. If again, we have everything in factored form, we can reduce out the x plus 3 here, and that gives us an x minus 2 left over. So the graph of this actually looks like y equals x minus 2, and there's a hole at x equal minus 3, and y then would be minus 5. So there'd be a little hole there. Okay. Let's take a look at if the denominator cannot be factored out. If the denominator can't be factored out and reduced out, then the points not in the domain are called vertical asymptotes. A vertical asymptote is a location of discontinuity. The graph can't touch it. And as they approach the vertical asymptote, they can get as close as you can imagine without ever going over it or touching it. Okay? And on a vertical asymptote, okay, as x approaches the vertical asymptote, the y values either go to infinity or negative infinity. Okay? So first off, let's look at this next one. This would be f of x right here equals x minus 4 over x squared minus 5x plus 6. So we'll find the domain. To find a domain, we'll factor the denominator. So x squared minus 5x plus 6 equals 0 means x minus 2 times the quantity x minus 3 equals 0 when we factor it out, which means x equals 2 and x equals 3. You could use the quadratic formula as well. This means that the domain will go from minus infinity to 2, our first bad point, if you will, has to jump over that point and start again on the other side of the asymptote at 2 and go to 3. Has to jump over 3 and start again at 3, just beyond 3 rather, and go to positive infinity. Okay? And we connect these with union signs. Since there are no common factors in the numerator and denominator, we can't reduce. So that means there's a vertical asymptote at x equal 2 and x equal 3, okay, where those two values are not in the domain and you can't cancel them out or factor, reduce them out. Let's take a look at horizontal asymptotes. To determine a horizontal asymptote, we look at the polynomial. we're going to define a polynomial this time as f of x equals p of x over q of x. They're both polynomials. And we have a to the n sub n, x to the n, plus so on and so forth, a sub 1x, a sub 0. For p of x, that's just a polynomial of n degree. And then the denominator, q of x, is b sub m, x to the m, plus so on and so forth, b sub 1x plus b0. That's a polynomial of degree m. A sub n and b sub m are the leading terms. These are important when we look at horizontal asymptotes. If n, the degree in the numerator, is smaller than m, the degree in the denominator, we have a horizontal asymptote at y equals 0, or in other words, the x-axis. If n equals m, in other words, the degree of the numerator, polynomial, and the degree of the denominator, polynomial, are equal, then we have a horizontal asymptote at a sub n over b sub m. And if the degree of the numerator is greater than the degree of the denominator, we have no horizontal asymptote. Now, what does a horizontal asymptote do? A horizontal asymptote describes the end behavior of x. In other words, as x approaches positive or negative infinity, what happens for y? It approaches the horizontal asymptote. Okay? Find a domain, vertical and horizontal asymptotes for f of x equals 7 over x minus 3. F of x equals 2x minus 5 over 3 minus x. And x squared plus 3 over x squared plus 5. So let's look at, and those would be good examples for you. So if we look at x minus 3, okay, 7 over x minus 3. Okay. The domain is every place except x equal 3. Since we have no vertical asymptote, or since we have no way to reduce that out, we end up with a vertical asymptote at x equal 3. Horizontal asymptote, let's look at the horizontal asymptote. What's the rule again? Well, the degree for the numerator is 0 with the 7, and the degree for the denominator is 1. So let's go back up to our table here. When the degree of the numerator is less than the degree of the denominator, we have a horizontal asymptote at y equals 0. So that gives us an idea where our asymptotes are. Looking at B, we have 3 minus x in the denominator, so our domain is every place except x equal 3 when I set 3 minus x equal to 0. Okay. Now, when I look at this, the degree of the numerator and the degree of the denominator are the same. They're both 1. So that means that if they're equal, our horizontal asymptote would be leading term over leading term. So what's the leading term in the top? It's the 2. What's the leading term in the bottom? It's this minus 1 in front of the x. So 2 over minus 1 would be negative 2. So we'd have a horizontal asymptote at negative 2. For C, we have the same degree in numerator and denominator. When the same degree in numerator and denominator are in place, for the horizontal asymptote, we take leading term over leading term. So that's going to be a 1 in front of the x squared over a 1 in front of the x squared, or just plain old 1. For the domain, if we look at the domain, x squared plus 5 cannot equal 0 in a real number sense. So the domain here would be all real numbers. You're not going to be able to square something and get minus 5, okay? As long as we ignore the fact that complex numbers exist, and we're not interested in that at this point. Okay, so there's no vertical asymptote. Let's try D, f of x equals 3 over x squared minus 9. So let's see, what would the horizontal asymptote be there? So let's see it. For the horizontal asymptote, the degree of the denominator is 2, the degree of the numerator is 0. So the degree of the numerator is less than the degree of the denominator. When that's the case, going back up here to our table, we find that the horizontal asymptote is at y equals 0. For the domain, we look at, okay, we have 3 over x squared minus 9. Okay, I'll factor x squared minus 9 as x plus 3, x minus 3. I set it equal to 0. That means I have a domain of x equals everything except when x is equal to 3 and x is equal to minus 3. So our domain would be negative infinity to minus 3, union negative 3 to 3, union 3 to negative or to positive infinity, where we have open ends in all the cases. We'll have a vertical asymptote at minus 3 and at 3 because those cannot be reduced out. So for this case, what I did is I looked at the table to look at how, if I go back to my original problem, okay, my original problem 7 over x minus 3, okay, I look at the table and I approach the 3 from both the left and from the right. Okay, so as I approach a 3 from the left, I go 2, 2.5, 2.9, and see what happens. So we can see as we get closer and closer to 3 from the left, x tends toward, or y tends toward negative infinity. If I approach it from the right, what happens is I approach from the right, I go down toward 3, and we can see that y gets larger and larger. So as I approach from the right, y goes to positive infinity. So let's look at this one. We have 2x minus 5 over 3 minus x. Okay, we're practicing safe algebra. We're going to put this into our calculator by using parentheses. Okay, I have a vertical asymptote at x equal 3 because 3 minus x means my denominator would be 0 when x equals 3. So I approach 3 from the left, from the right, and from the left. As I approach from the left, we can see it gets bigger and bigger, so it heads toward positive infinity. As I approach it from the right, we can see it gets smaller and smaller, so it heads toward negative infinity in terms of y. Looking at D, we have 2 scenarios. We have minus 3 and 3. So as we approach minus 3 from the left, okay, we start with minus 3.1 and head toward minus 3.0001. We can see it gets bigger and bigger. So as I approach 3 from the left, as I approach that vertical asymptote, I head toward positive infinity. As I approach minus 3 from the right, I head toward negative infinity. Now, what about the 3 and from the left and right? So from the left, when I approach 3, I head toward negative infinity. And then from the right, as I approach 3, I head toward positive infinity. How do we graph a rational expression, or function rather? First, we find a domain. We find any vertical asymptotes, any horizontal asymptotes. We use a table to analyze how the function behaves at the as it approaches the VA, I mean the vertical asymptote, from both left and right. And we also find the x and y intercepts if they're available. Sometimes we don't have an x or y intercept. So what I'm going to do is I'm going to graph a couple of these, and I'll send these out as a PDF so you can check yourself to make sure you're on the right track. Until then, take care, and hopefully this helped you a little bit.